Very much for the kind introduction. Let me see. Yeah, that's desktop I want to be sharing. So good. Do you see the slide?
Yeah, we can see that.
Good.
Yep.
Okay. Yeah. So thank you very much for the kind invitation also to present our research here. The title is fairly bold, as you may have noticed, and it also is clearly quite applied. But I thought it can be also interesting, especially if it's a broad audience with different backgrounds, because you'll see that this goes in very many different directions. But it's all based on what you're seeing here in this movie. This is a shell, a thin shell, like you can imagine like the peel of a fruit, peel of an orange or an apple or something like that. But in this case, that shell is made of a liquid crystal that is called a cholesteric liquid crystal, hence the title. And it's surrounded by water on the inside and water on the outside. And you see it gives off rather striking colors in peculiar patterns. And this started out a couple of years ago with us just trying to understand where these colors come from, or rather these patterns. We knew the color that's well known, that cholesteric liquid crystals gives rise to colors, but the patterns were very surprising. So it has been a journey of a couple of years where initially it was just curiosity research trying to understand the pattern formation, and then improving the production or our methods for making these shells, and also turning them from the liquid crystal into a solid. And as we got, as this journey continued, we realized that there are actually plenty of interesting uses of these shells. And so what I'm going to be talking about today is to first give you a super short crash course into what liquid crystals are and what cholesteric liquid crystals are and why these colors arise. And then I will try to give you a feeling of, at least, of how we can apply these and why. And for instance, in working against counterfeiting, which is a huge problem today, and also in track and trace, which is a very important part related to counterfeiting also, but also in general very important for supply chain management and logistics, and many other things. And I'll talk a little bit about that. And related to that, or the way we are applying these in track and trace are also equally useful for supporting autonomous robot operation and augmented reality. And finally, there are potential in search and rescue operations and in disease testing. And if you see this slide, you think this cannot possibly be the one and the same talk. They are so diverse opportunities, but actually it is. And it all arises from these optical properties. And that's what I'm trying to convince you to, that these optical properties are so peculiar that they really give a lot of opportunities that can then be applied in very diverse areas. So as I said, it's all based on the shells here. So I'm first going to talk about this, but I would like to thank all my collaborators, and these are not all of them, but the key senior collaborators at least, because if you think about how diverse the topics of this study is, you cannot do this alone. That would just be unrealistic. So it is very much thanks to Matthew Schwartz that this all got started, I would say. He's an artist and architect specializing in design and construction of the built environment, and is very much involved in robotics for doing that. And Gabriele Lenzini here at the University of Luxembourg, he's specializing in computer science or security, reliability, and trust, and from a computer science point of view. And Holger Phas is also here, and he's working with robotics and automation. Then Benny Mantin is a more recent collaborator who is leading the Supply Chain Management and Logistics Center here at the University of Luxembourg. And Carol Lindster and Shiva Krishnamurti, they are our collaborators on the disease detection project, because Carol is an expert on the proteins that we would be working with, and not only proteins, but viruses and so on in general. And Shiva is an expert in immobilizing biomolecules onto various surfaces. So these ideas we've had that I mentioned, they've kind of developed very much in collaboration with many different people, but then to really conclude that they are realistic, for that, it has been very important to work with the people who are really expert in the field. So it's also an example of how interdisciplinary collaborations can be very fruitful. Not always easy to find the same language to speak, but it's really, really interesting. So I'll come back to their contributions in a moment. But first, a little bit for anyone who might not know what a liquid crystal is, a very brief introduction. So we all know what liquids are. They are fluids, they flow, they can take the shape of their container or many other shapes. They have, if you look at them at the molecular scale, you will realize that they have only short range order of the molecules, which makes them isotropic. So their macroscopic properties are the same no matter how you investigate them, for instance, with regardless of polarization or direction of light and so on. And this makes a very strong contrast to crystals, which is the equilibrium state of solids. Of course, we also have glassy solids, but if you have crystalline solids, glassy solids are not in equilibrium. So if you have equilibrium solids, they are in a crystalline state. And those crystalline states are characterized by long-range order of the molecules or atoms making up the crystal. And it's in a lattice, and this gives you always anisotropic properties. Don't have to be anisotropic optical properties. It depends on which tensor you're dealing with, but and which the crystal structure is. Cubic crystals are optically isotropic, but the crystals are always anisotropic in higher order tensors. And many non-cubic crystals are also optically anisotropic. So this distinction between isotropic and anisotropic is often how we determine whether something is whether something is long-range ordered. And how do you determine that? Well, you typically put the sample between crossed polarizers in an optical microscope. If you look, at least if you focus on the optical anisotropy. So a polarizer is you have them in sunglasses and so on. So it's a filter that filters out a certain oscillation direction of the electric field. So if it's a linear polarizer, at least, and if you use one polarizer after the lamp, then the light after that polarizer will be oscillating, the electric field will be oscillating in a certain direction, and the crossed polarizer then will only let through light in the perpendicular direction, which means that if there is nothing in between, nothing will get through the second one, and therefore you have dark. And the same thing holds if you have an isotropic material in between, because the isotropic material does not change the state of the polarization. But an anisotropic material can change the state of the polarization. It can give elliptical polarization, circular polarization, or a different orientation or linear polarization. So you often see then that a solid crystal will be bright between cross polarizers. Now, with this in mind, we can then look at what a liquid crystal looks like in between cross polarizers. And that's what you're seeing in this video. It's actually, we are cooling the material. So you often have a phase transition from a regular isotropic liquid at high temperature, and that's where this starts right now, where it's black. And then we cool down, and then you have a transition to, in this case, the simplest liquid crystal phase, which is called a nematic. And you can clearly see there are colors. So this shows that this is anisotropic, but you also see that it flows. So what I'm doing here is I'm just touching the cover slip with the spatula very gently. And you see this, this clearly flows, so it's a liquid. And this is almost contradictory combination of fluidity and long-range order. That is what is characteristic of liquid crystals, which is in many respects is very surprising that you can have this, because the anisotropy of solid crystals is strictly related to their lattice. And here clearly you cannot have a lattice because you see it flows, so there is no lattice. So where does the long-range order comes from? Well, it actually comes from the molecular structure. So common to any liquid crystals is that their molecules are formed, they are anisotropic in shape or anisommetric. And the most common example is that they are rod-shaped. And of course, the real molecular structure is more complex than this, but because you have also very fast rotations about the long axis, we can often approximate them with an ellipsoid, something like this. And when these molecules are collected in a condensed liquid phase, you can have a temperature range where it is actually favorable for them to align along a common direction. So the exact origin is not trivial to explain, but for what we call a thermotropic liquid crystal phase, where this happens on its own, it's related to the anisotropy of the van der Waals interactions in these very anisotropic molecules. And the important thing is then that although this is a liquid, there is no long-range positional order, there is no lattice, the molecules tend to align along the same direction. And because the molecules are anisotropic in shape, we then get very different properties along the alignment direction compared to perpendicular. And this gives us this anisotropic behavior. And if we then, in addition, add what is called a chiral dopant that breaks mirror symmetry. So chirality means screw shape, basically, or an example of chirality is screw. Chirality means absence of mirror symmetry. And the most common example that we all know is a screw. And indeed, what happens when you add a chiral dopant to this kind of liquid crystal phase that we call a nematic, it then becomes a chiral nematic. And what happens is that this orientation, the long-range order orientation that we call the director, that starts rotating along an axis that is perpendicular to this orientation direction that we call the director. And we get a helical modulation of this. And because the optical properties are strictly determined by the orientation of the molecules, so you have what we call an extraordinary refractive index if light is polarized along the long axis along the director, and we have ordinary refractive index if it's perpendicular to the director. And then you see that if you have this type of helical modulation, if you send in light, for instance, that has a polarization like this in the horizontal plane of the screen, then you see you would have extraordinary refractive index here, and you would have ordinary here, and then again you would have extraordinary and so on. So you have a modulation, a periodic modulation of the refractive index. And that means that light will experience this material as a periodically structured material. And you then have what we call Bragg reflection that you may have heard of with respect to X-ray scattering. That's what Bragg originally developed his theories for. But it happens at any time that radiation enters into a periodic medium, an ordered medium with a periodic structure. And what the outcome of this is that you get very strong reflection because light cannot propagate if the wavelength matches the apparent period in the structure, depending on, and the apparent period, of course, depends on the angle with which light enters with respect to this helix in this case. So what effectively happens with these types of cholesteric liquid crystals, if the pitch, the period of the helix, the pitch is short enough, which typically means a few hundred nanometers, then if the light enters exactly along the helix, then the wavelength that cannot propagate is the wavelength that has that is equal to the pitch in the material. So which means if you take, for instance, red light is about 650 nanometers in wavelengths. So if the 650 nanometer wavelength is reflected for normal incidence along the helix, then the pitch of the helix is actually a bit shorter because the refractive index, the average refractive index, is larger than 1. But anyway, the point is that for this orthogonal incidence, the back reflection is then the longest wavelength, so that would be red. But if you have inclined incidence, then the slightly inclined reflection is then blue shifted to slightly lower wavelengths. And if you continue this, you then see that it goes from orange to green to blue. This is the same sample that we just look at along different orientations. So this is red if you look at it straight on, and as you incline, change your viewing angle, then it goes from red to blue. And in addition, which is very important for the applications I'm going to tell you about, the helical structure changes the polarization or polarizes. Even if it's unpolarized light coming in, the reflected light is circularly polarized with the same handedness as the helix. So if it's right-handed helix, then you have right-handed circular polarization being reflected. And circular polarization is very rare in nature, but very useful. So if you go out on the street today, or if you just look around your office, very likely nothing that you see is circularly polarized. But if you go to the cinema and you watch a 3D cinema, you typically put on these goggles. And what those goggles are, they are circular polarizers. So in the cinema, there are actually two projectors showing two movies. One movie is for your right eye, the other movie is for your left eye. In order that your brain doesn't get confused, you put on the goggles so that the right eye sees the correct movie for the right eye. And that is because that projector is projecting the movie with right-handed circular polarization, and your right eye has a right-handed circular polarizer. It blocks the movie for the left eye because that movie is projected with left-handed polarization, which is instead then let through by the polarizer in front of your left eye. So that's the neat thing with circular polarization. You can actually superimpose light of showing different things, but you can just filter out one particular message if it is circularly polarized. So that happens in the 3D cinema, but it also happens with cholesteric liquid crystals. So these are now these shells that we prepared with cholesteric liquid crystal. And here you see the shells through left-handed circular polarizers, and you can see the shells are there. We have increased the intensity a little bit, so we still see some scattering, but there's no color. The color appears only when we look through the right-handed polarizer because the polarization, the reflections are right-handed polarized. And that's going to be very, very useful for how we use these. But what I didn't really mention yet is, well, how do we make these shells? And why is it so important that you have a liquid crystal structure giving rise to this? So the liquid crystallinity is not just fascinating, that you can have this type of order spontaneously arising in a liquid, which is kind of counterintuitive, but it's also super useful because since it's a liquid, you can process it just like you can any other liquid. So you can flow it, you can shear it, and so on. And that allows us to make these shells. We wouldn't be able to do it otherwise. And the way we do it is we use what is an approach called microfluidics. So this is a high-speed movie of this. It's a very fast process. So here we have slowed down the process. And what we do is that we flow an inner water phase inside. This is a capillary, a sharp capillary, and around that capillary is flowing the liquid crystal phase because it's a liquid, right? We can flow it. And against this liquid crystal phase is we flow another water phase. And the water phase and the liquid crystal phase, they don't mix. It's like oil and water. So here you have a boundary where if you match the flow speeds correctly, you get what is called flow focusing. And therefore, this compound flow of liquid crystal around the water is then focused into this collection capillary, and everything is suspended in water again. And then we get this water droplet inside a shell of liquid crystal, and everything is suspended in water again. So that's how we make the shells, and it wouldn't be possible if we were not using a liquid phase to begin with. Another interesting thing with this is that because we have two different phases, we have a water phase here, and then we have the liquid crystal phase as a shell around it. These are different phases, so they don't necessarily have the same density. In fact, they almost never have the same density. And we are on Earth, so gravity affects what we're doing. And that means that if, for instance, the liquid crystal is a bit lighter than water, then the water droplet will sink to the bottom and make the shell thinner at the bottom and thicker at the top. If the liquid crystal phase is instead denser than the water, then it will be the other way around. And this asymmetry of the shells turns out to be very important for the way we make the shells in the end. Okay, so we make these shells with the cholesteric liquid crystal phase, making out this part. And when they are freshly prepared, they look something like this. So this is in transmission microscopy without polarizer. And you can see it's pretty messy. There are lots of defects. And here you see the reflection. You see some color, but it's really not at all very regular and not good control. And that's because, yes, we can make the shell, but this helical structure, it takes some time for it to organize in the way we want it. We want the helix to be radial in the shell. That way we get a nice spherically symmetric optical element. And what we do then is we use something called osmotic stretching. We simply prepare the shell with some solute inside that is not present on the outside. And these shells, they are not miscible with water, but that doesn't mean that water cannot go through. So it's like a semi-permeable membrane, and you then have an osmotic pressure that actually drives water from the outside into the inside. And if you then wait a little bit, you see that the shell gets larger and larger and larger and thinner and thinner. And this stretching actually aligns the helix. So from this messy structure that we began with, we have a very regular reflection pattern that is produced by a radial helix within 12, at this point in time, this was 2016, it took 12 to 24 hours. We are now down to 6 minutes if you change the osmotic pressure. So this can be much better advanced. So that's very important for that you can get the optical properties controlled. Now, the other thing is that if you want to use these cholesteric spherical reflectors, we call them CSRs for short, in something, then in the end, you cannot work with the liquid state. The liquid state is super important in order that we produce them. But then if you want to use them, they have to be solid. So we have to polymerize them. And that is an interesting process in itself. So here you see these shells before polymerization from the side. So you can clearly see what I mentioned with the gravity-assisted asymmetry. So these are a bit thicker at the bottom and they're thinner at the top, all of them. And when you polymerize a reactive liquid crystal, it shrinks a little bit. But now you have a shell that's going to shrink, but it surrounds an incompressible fluid, liquid water. So what's going to happen? Well, what happens when you polymerize them is that because of this shrinkage, they distort. And you see, because you have this thin part at the top, that's where the water will kind of try to bulge out, because that's the least resistance from the polymerized liquid crystal. And then if you, after this, rinse in acetone, which we need to do anyway, because we need to get rid of the a little bit unreacted components, then the acetone swells the shell again, and then this swelling creates a strain that this bulged out part cannot sustain. And so they all break off. And we end up with these shells with a little hole at the top. One single hole in every shell, which is very important. I should say that they all look like ellipses here. They are not ellipses, they are spheres. It's just because they are at the bottom of the capillary and you have a bit of optical distortion there from the capillary. So this is what they actually look like in the electron microscopy. You see they're perfectly spherical and there is a hole, one hole in each of these CSRs. And that hole is very important because if you look at them in optical microscopy, you see that in reflection, we have these nice reflection colors. But in transmission, you see there is a lot of scattering. And that scattering is due to a polymer called polyvinyl alcohol, or PVA, that is collected on the inside surface. We need that polymer for producing the shell, otherwise the interfacial tension will pop the shells. So you need the polymer in order to have stability. But right now it's making a mess because it causes a lot of scattering. But now this hole is so useful because we can now rinse these with water, and then the water dissolves the PVA, and we get rid of it, and there is basically no scattering left. So, and that's of course very important if you want to use this optically, that you don't have any scattering. So now we can use these, but let me first of all just tell you a little bit where these patterns come from. So this is a collection of CSRs, and you have one in the middle, and it's surrounded by other CSRs in a hexagonal arrangement. And at the moment, I hope you can see that there is a slightly brighter circle roughly in the middle. That's the area that we are actually illuminating. This is reflection microscopy. So light comes from the top and we are looking through the same objective that we are illuminating through. And you see here that the illuminated area has no reflection except right in the middle. That's the center of the CSR that we are illuminating. So that's retroreflection. The light comes along the helix. It sends, the helix reflects the light back, and it's with the longest wavelength, which in this case is red. Then you see outside the illuminated area, there are green reflections and eventually red-orange reflections in a hexagonal pattern. And to understand where they come from, we open the aperture. So right now we have the smallest aperture and we have only this part illuminated. And now we open the aperture and you will see that we illuminate larger and larger area. And as soon as we start illuminating the neighboring shells, then you start getting reflections in the middle shell. And then the more you open, the more reflections you see. So what is happening here is a kind of optical cross communication that because it's a sphere, this central reflection that only happens when the light it reflects at the top of the shell and it goes right back. But of course, light can come here at the side, and then you don't have reflection back because it's a sphere. You have reflection horizontally instead. And then this horizontal reflection reaches another shell, and that one then reflects back to us. But this is Bragg reflection we are dealing with. So when you have retroreflection, that's 0 reflection angle. But here it's 45-degree reflection angle. So that means you get a blue shift, and that's why for the same shell you get red in the back reflection, but you get green in the side reflection in this communication pattern. And another interesting thing is that if this was always so far for illumination along the shell along the vertical direction, and here is another sample where we have these red spots at the center of every shell, and then you see here it's a bit more blue in the communication channel. These are the spots that are arising from communication between the shells. But if you change the illumination direction by not illuminating from the top as usual here through the objective, but we turn off the lamp of the microscope and instead we put a lamp next to it and we illuminate with 45-degree angle, then this same sample looks like this. So it's the exact same sample. We just illuminate at 45-degree angle instead, and everything changes. The colors changes. We get the The main spot is not in the center anymore, but it's a little bit shifted upwards. We get new communication patterns and so on. So it's very safe, sensitive to how you illuminate it. And what the security researchers called this type of behavior is that you have many challenge response combinations. So the challenge is, how do you illuminate it? For instance, which direction do you use, or which area are you illuminating? And the response is the pattern that you get. So that is already an indication that this could be useful for some kind of authentication device, because this is what one way of the classic way of authenticating is that you have a challenge and you have a response, and the response has to be correct for the challenge in order to authenticate. But there is another aspect that is quite important, and that is that the asymmetry of the shell, as I mentioned in the beginning, also affects the optical properties. And I showed already that it affects the mechanical properties. But if you look at this shell here, that this is from the side, it's thick at the top and thin at the bottom. If you look at it from the top, you get the pattern that we have been talking about so far, with the reflection in the middle, that's the retroreflection, and you have this communication pattern from the sides, that's communication with the opposite, with the neighboring shells. But if you turn the shell around, so the thinnest part is at the top, then it is so thin that light enters the shell, because you need a certain number of pitches to get all the light reflected. So if it's too thin, it goes through a little bit, but then it hits, so it here, for instance, it enters here, but then it hits the thick side on the inside. And there you can have many different types of reflections that eventually kick out the light on the other side. And this type of internal reflection, it gives you an optical echo chamber, if you like. And because it's a shell, these reflections appear as rings. So again, the exact same shell, just illuminated from the top or bottom, can give you this type of pattern with the spot in the center and the communication spots, or this type of pattern with the spot in the middle and rings around it. And this, of course, also works for many shells. So this is a sample where you have all the shells arranged with the thick side upwards. And the same sample viewed from the other side gives you this type of reflection pattern instead, because now you get the internal reflections. So you have a lot of different patterns being produced by these CSRs. And we can then also combine CSRs with different pitches. So this one, for instance, has a bit longer pitch than this one. So the central reflection is red. Here it is in the green because it's a shorter pitch, and so on. And then you get not only different central spots, but you also get different cross communication. Here you have green, yellow. Here you have blue. And that means that if you combine different CSRs randomly, you get really a unique pattern, which then, in addition to having the different pitches, you also have then different orientations and so on. And that means that every arrangement is unique. And in addition, it's also basically impossible to clone, because you have so many different challenge response function, because the pattern changes depending on illumination. And that's where it gets really interesting to do something against counterfeiting with these. So what we want to do is we make coatings of an object that we want to confirm that this is authentic, it's not a fake. And this coating contains these CSRs arranged in a random way. And this is then recorded as the authentic one. And then when the receiver, a customer or a receiver on the other side of the world receives it, they can check what is the optical reflectivity pattern. And if it's not the authentic one, then they know that something has, this is not an original one. Is this important? Yes, it is. I'm not going to go through the slide in detail. It's just to give you a highlight. This is a very recent report from June this year from the OECD and European Union. It's a report on the global trade in fakes. And it's really very, very significant. It concerns a lot of money, and it concerns health. You see the COVID-19 pandemic is mentioned. The most striking thing is perhaps that there are quite a few people in the world who have been, they thought they were vaccinated, but they actually got salt water in their veins. And of course, there can be much worse things. There can be absolutely dangerous things being sold as medicines and so on. So counterfeiting is enormously important. It affects everything. These are just some examples. So medicine is this is probably the most that everyone knows, Viagra. Very popular to counterfeit, of course. But of course, clothes, luxury goods, shoes, clothing, and so on. Toys, very popular to counterfeit. Electronics, you may save your PhD thesis on a memory stick of some kind, and then the next day it's gone because it was a counterfeit memory stick. This is Tamiflu, again, medicine. Wine, very popular for counterfeiting. This is pet food. These are airplane parts. And this is maybe the most scary, that counterfeiting is also important to know that when we speak of counterfeiting, this is not when you go into a sleazy back street on your holidays and you buy a Rolex watch for 20 bucks, you obviously know this is fake. Counterfeiting means that the customer pays the price of the real product, thinking they get the real product, but they actually get something counterfeit. And this even affects the airplane industry. So an airline may be buying spare parts for their plane, thinking they get the original, but it's actually counterfeit. So it's very, very serious. And how do we then do something about this? Well, what we are working on now is really to make these coatings on the object that should be protected. And the important point is that it's a random arrangement of these CSRs. And because it's in a liquid, but it's not in any liquid, it's in a UV curable binder. So you shine UV light on it and it turns from a liquid to a solid, and it goes very quickly. So that's a nice thing, that you can have this random arrangement, and before it has a chance to reach an equilibrium arrangement, you turn it from liquid to solid, and thereby you lock in this random arrangement. And you really have a unique, unclonable, and tamper-proof fingerprint, which is really very, very useful for this type of application. The computer security or the security researchers call this a physical unclonable function, or PUF. You may have heard of it because it's getting very popular in the literature now. And compared to many other anti-counterfeiting solutions like holograms and so on, an important point is that not even the producer could make a second copy because there's so much random, unpredictable components in here. So the second application that I mentioned was the supply chain track and trace. So supply chain, that's a term used for all the objects that go into a product. Let's say you buy a car. That, of course, consists of a lot of different items, and they have been produced all over the world, and they are eventually being assembled together. But the supply chain is how are these being brought together? And it can you even speak of supply chain for even the final product. So we had supply chain problems during the COVID-19 pandemic, and that's why we didn't have face masks and so on. And because the items are being transported across the globe, there's a lot of opportunities for bad actors to introduce underperforming items, fake items, just broken items or whatever. And therefore, there is a lot of work in being able to label a certain item so you can track it through the supply chain. So you know where it is and where has it been, and you know that it's this item. This is usually done with barcodes or QR codes. The problem is that it's as easy to produce a fake barcode as QR code as it is to produce the original one. It's very easy to reproduce them. So we want to do this with CSRs. And there is another advantage with this. And now we are not talking necessarily about the individual, the random arrangements, but we're talking about the retroreflection. So retroreflection means that no matter how you look at it, if you send light in a certain direction, you get the same light, the same response back. So you send in light, white light here, for instance, these are blue retroreflecting CSRs. No matter how you look at it, you get a blue reflection back from every single CSRs. And this is something that is really useful, and you can understand that because we already have a lot of retroreflectors in our society. So traffic signs are typically retroreflectors. A lot of fancy clothing are retroreflectors. We have these safety vests in our car, for instance, that are retroreflectors. But standard retroreflectors reflect all light, that they should be visible, right? So they reflect white light, any wavelength. So they're very bright. If you do retroreflectors with cholesteric liquid crystals, you can tune so that only blue, for instance, is retroreflected, or only red is retroreflected, or the most interesting, only infrared or only ultraviolet. And that means that these are retroreflectors for machines that can see infrared or ultraviolet, but for us humans, they are invisible. And that means that we can actually hide these retroreflectors. And in addition to that, we have the circular polarization that I mentioned. So let me show why this is important. Here you have a tag that we made. It spells the letters ESMP. This is in blue reflecting CSRs on a black background, and here you have infrared reflecting CSRs. You can see it's not perfect because they have some scattering and they are handmade, but it's pretty close to only blue and not too much visible in the infrared case. And this is on a white background, and you can see that they are fairly invisible. And I should point out that these are actually imaged for maximum visibility. So if you just look with your eyes, you really have difficulty to see them. So here is the blue reflecting sample put up in a regular office environment. It's my postdoc office next door here. And the photograph is taken through a right-handed polarizer. Now, if we then take, and that's the slide just to point it out. If you then take a photo of the same environment through a left-handed polarizer, then the ESMP letters are quite a bit darker. You only see the scattering. Much of the blue light is gone. And what we do now is we subtract these from each other. And because basically nothing is circularly polarized in our environment, everything is removed, because the unpolarized components, they appear equally in both images. So when you subtract them, they are gone. What remains are the letters. And if we then filter out the blue channel and make it white to have a high contrast, we see that we get this message with very high contrast, even in a very busy background, because we can remove the background. So what we are now doing is we are making QR codes, and we're making other types of barcodes and so on using these markers, because the nice thing is then we can, for tracking, for helping supply chain tracking, we can then label these with invisible codes that are very easily read by machines, thanks to the circular polarization. And I see I'm too slow, so I think I'm just gonna jump over a few slides and just mention that this is very useful also in robotics. What I want to highlight here is these are some videos from Boston Dynamics. You see these codes markers here on the doors. These are called fiducial markers. They look a little bit like QR codes. They are black and white. They are super useful for robots in order to make sense of their environment. The problem is that they're really ugly. So that's why you only have them in labs, in research labs. So what we're doing now is we're making these markers using invisible CSR reflectors. And that way, robots can use this type of fiducial markers for navigating, but we can put them in the everyday areas where we are living and working because we don't see them. So that's a very nice opportunity as well. And as a final example, I'll skip the search and rescue because it's fairly straightforward. It's not so important. But let me just end with the medical testing. So you probably all have used these rapid antigen tests by now. You may know how they work roughly. So it's you put your sample on a paper strip, and this then flows along the paper strip, and you have these antibody labeled fluorescent, sorry, not fluorescent, gold nanoparticles. that give a violet color. And if you are infected, the virus is in the sample, then the antigen locks onto the antibody, brings the nanoparticles with them, and there is then this strip that shows that you have been infected. That is then also, you have these immobilized antibodies also there, and then the virus particles basically tether the violet particles to the strip, and that's how you see that you have been infected. This works very well. The problem is that the color response is pretty weak because you have white background and you have pink response. So this means that you need a lot of virus particles to get a clear response. And for this reason, there is a little bit of question, or it's not completely clear that you can really trust this, because you need such enormous virus loads to really have a positive response. So in the latest project, we are actually replacing the gold nanoparticles with CSRs, because the circular polarization allows us to subtract the background, and therefore we get much, much better contrast, which means that we expect at least that we will have a much lower sample load required for getting a response. So let me just conclude then by saying that cholesteric spherical reflectors can be made based on the nature of liquid crystals. They can be made invisible to the human eye, practically at least, but they remain detectable by machines with the appropriate circular polarization and infrared or ultraviolet imaging. When you view them close up, you have this very rich set of optical challenge response functions that allows you to uniquely identify one from another. But by depositing many of these into certain patterns like QR codes, barcodes, fiducial markers, we can then also use them in supply chain management and supporting autonomous robot operations. Augmented reality use the same fiducial markers, so I didn't mention it, but it's exactly the same thing. And potentially also raise the sensitivity of rapid antigen tests and so much more. So my postdocs, Yongeng Rijesh Kidakidatadat and Hakam Aga, are very much thanked for all their work on this. ERC and ONRG are funding, as well as FNR. And I'll just leave this slide as the end. These are the papers where you can read more, because this was just a rapid overview. So thanks very much for your attention, and sorry if I was a bit too slow.